All right, welcome back. So in this session, we are going to take a look at introducing a concept of integration via substitution. Essentially, this provides a technique for us to undo the chain rule for derivatives. So just to sort of remind ourselves of the chain rule, admittedly, what is in this blue bubble is probably what you had seen initially whenever you had seen the chain rule. The chain rule is essentially a derivative rule related to composition of functions. When you have a function inside another function, essentially having two functions chained together, you take the derivative by first computing the derivative of the outer function, leaving the inner function alone, and then you multiply by the derivative of the inner function. A way to sort of take this expression classically seen that has so many parentheses and sort of like minimize the number of parentheses so we don't have to see f of g of x. If we just replace that inside function with u, I guess it reads slightly profane as fu, but it ultimately computes with a little bit more conciseness. So the derivative of a function of u is just f prime of that function of u times u prime. So same idea going on here in each of the factors to say initially we just take the derivative of the outer function, leaving the inner function alone, and then we multiply by the derivative of the inner function. So, just to remind ourselves of sort of an example that you could see here, what if we took the derivative of like sine of 3x? Well, note, this is not just sine of x, right? This is sine of 3x. We've got a function inside our function. So this is a classic application of the chain rule. And whenever we apply the chain rule here, we first take the derivative of the outer function, the sine function, leaving the 3x alone. So that'll give us what, like cosine 3x? But we don't stop here, right? Because we have to multiply by the derivative of the inside function, the u prime, which would be the derivative of 3x, which is 3. So here is an application of the chain rule just using derivatives. Now, if we are going to play the integration by substitution game, we are going to be trying to undo derivatives that have resulted by way of the chain rule. So down here in these two examples, at least to get us sort of warmed up, here are two examples of functions that result via the chain rule, which is to say, because when you integrate, right, you're essentially asking what function has a derivative of what's inside the integral. And well, to think about it in this first example, because we have, note, a function inside another function, we've got an x squared inside the cosine function. And then also note that we've got a derivative of that x squared hanging out nearby. You can essentially think of the x squared as u, and you can think of the 2x as your u prime. And if you do, then essentially what we are doing here is trying to undo a chain rule. And if you think about the function that would have produced this cosine x squared times 2x via the chain rule, it would have to be not the cosine function, but the sine function, or at least based on the sine function, but not just any sine function, because the thing that is inside the sine function needs to be x squared. Throw on the plus c by necessity, and check it out, sine x squared plus c. If you took the derivative of this, of course the c is going to go just drop off. And when you take the derivative of the sine x squared, using the chain rule, we first take the derivative of the outer function sine to get cosine. We leave the inner function alone, x squared. And then we multiply by the derivative of what's inside, 2x. So really, analogously to this cosine 3x times 3, is this expression cosine x squared times 2x. And so if you can sort of see that analogy there, you're sort of setting yourself up for tuning your eyes to what you need to recognize whenever integration via substitution comes into play. What about this last example? Again, just to sort of like get the wheels turning here in our brain, looking at this function, you can notice that we have a function inside our exponential function. Our exponential function is not just e to the x, no, but e to the x cubed. If it's easier to see, you could almost put parentheses around that x cubed, because truly the x cubed is sort of like inside the exponential function. But now, by virtue of that x cubed being inside the exponential function, a chain rule for derivatives would occur if there was a 3x squared hanging out within the same expression, which indeed there is, right? So if you think of what's inside that x cubed as your u, then you can think of that 3x squared as your u prime, and everything would work out really nicely via the chain rule. So what function would have this 3x squared times e to the x cubed as its derivative? Well, that function would have to be the exponential function e, right? Because the derivative of the exponential function is just itself. But then what would be in the exponent but x cubed plus c by necessity, right? So if you were taking the derivative of this resulting expression, right, the c would drop off. When you take the derivative of the e to the x cubed, you would simply get, well, take the derivative of the outer function, leaving the inside function alone, e to the x cubed, multiply by the derivative of the inside function, which would be 3x squared. And so the idea here is when we are integrating, in some sense, we are almost playing like a derivative detective. We're trying to determine what function would have the function inside our integral as its derivative, what function would have that derivative as its result. And hey, if you're in a situation where you've got a function inside a function, and then you've got an expression also within that function that is related by way of derivative, like this x squared and this 2x, or the x cubed and the 3x squared, those two factors that are sort of present there, then that could be a symptom of the chain rule for derivatives, and ultimately the method of substitution will come into play. So how exactly that method of substitution takes form, I'm going to pause here, sort of clean the slate a little bit, and then touch up on the technicalities, at least to get ourselves introduced to the idea. But actually these two examples which we've worked out will relate to sort of more intricate examples, as we'll see. All right, so continuing on discussing integration by substitution, let me sort of just tip us off to the features to look for in a function inside an integral, which would be an indication of the fact that the chain rule for derivatives would have occurred, that integration by a substitution would be in play. So first off, you should be on the lookout for some inside function, some function inside another function. So take the two examples that we worked out previously. The x squared is a function inside the cosine function, and the x cubed is a function inside the exponential function. So noticing an inside function is the first thing, and you almost want to think of that inside function as u in your head. You're not wrong for doing so. And then ultimately we want to be on the lookout for u prime, or in general, some constant multiple of u prime, some k times u prime, appearing as a factor elsewhere. So noting that our inside function u in our first example was x squared cosine x squared, that x squared was the inside function, well then the derivative of that x squared would be the 2x that makes an appearance. And then similarly the u was x cubed, and the derivative of x cubed was 3x squared, which also made an appearance as a factor elsewhere. Well, as I say here, that factor elsewhere doesn't necessarily have to be just u prime. It could be any constant multiple of u prime. And that works out because ultimately constant multiples sort of factor out of integrals, as we've seen from our properties previously. And so constant multiples are sort of nothing to fear when it comes to computing antiderivatives, when it comes to evaluating indefinite integrals. So take a look at this example up here, which we're going to work through here in short order. But well, if you look at this function, first note there is an inside function, right? There is a function 2x cubed, which is hanging out inside our sine function. So that is an inside function, and immediately we think of maybe u as being this 2x cubed. But now if you think of the u as being 2x cubed, the u prime is 6x squared, right? U prime should be 6x squared. So we don't have exactly 6x squared here. Let me get this on the slate here within view. So the u prime is 6x squared. Now again, 6x squared is not 10x squared, but 6x squared is very much related, right? We're only need an adjustment via some constant. I think in this case it would be a constant of 10/6, but whatever, so be it. We can actually work this out. And to work this out fully, let me just take a moment here. I'm going to take this chain rule expression. And instead of writing it as f prime u times u prime, I'm going to take this u prime and I'm going to replace it with du over dx. So replacing the u prime with du over dx is not changing the content of this chain rule expression, but it is helping us set up for the utilization of ultimately substitution. You'll see where that comes into play here in a moment. So the way that we'll proceed going through an exercise such as this is we'll first set u equal to that inside function, the 2x cubed. And then we will directly, applying the derivative, compute du over dx, the derivative of u with respect to x, which is this du over dx term here. Well, du over dx, what does that turn out to be? That turns out to be 6x squared. But now, so that we can substitute back into our original integral, you might notice there are no du's in the original integral. The integral was exclusively in terms of x. Now this 2x cubed could be replaced with u, no problem. But this dx is sort of a little bit funky because, well, the way in which we have dx showing up in our derivative expression is with a du as well. So what we do is we essentially multiply both sides by dx. It's a slightly egregious thing to do. It requires some study of differentials, but I'm not even going to get into that. What I'm going to just focus on is sort of an algebraic manipulation of this expression, so that instead of having du over dx, we have du equals 6x squared dx. In fact, if you note, you can imagine getting comfortable with derivatives using differentials, and ultimately you could get from u equals 2x cubed to du equals 6x squared dx in one step. But look, the long story short is this. Boy, if we just had 6x squared dx, we could substitute perfectly. But we don't have 6x squared dx, do we? No. We want this to be a 10x squared dx. So we want 10x squared dx. Now, how are we going to get 10x squared dx? Well, the only thing we have to do is adjust by a constant multiple. I want to cancel out the 6 and replace it with a 10. So what I'm going to do is I'm going to take this algebraic expression and I'm going to multiply both sides by 10/6. Just multiply the same number to both sides, 10/6 to both sides as it is. And, well, let me just put a partition here so that we're not confusing the equation on the left with the equation on the right. But now here, look, on the left-hand side, we'll have 10/6, or, well, maybe better, let's just write 5/3. We'll have 5/3 du is equal to, the 10 and the 6 will cancel, as desired, and we'll get 10x squared dx. Note now that 10x squared dx is exactly what is inside our original function's expression. The 10x squared dx is, well, now this 5/3 du. And, well, as previously mentioned, the u is just 2x cubed. So if we apply substitution appropriately here, so if we apply substitution, just algebraic substitution, two things that are equal to one another can be exchanged with one another with no loss of content. Applying substitution, I think I missed a syllable there. But anyways, right, what will we get? Well, where we see 10x squared dx, we're going to replace with 5/3 du. So that 10x squared dx is going to just be now 5/3 du. We've essentially replaced the 10x squared dx above with the 5/3 du down here below. And then what was inside, we also had the sine of 2x cubed, but now that's just sine of u. But check it out. This expression now requires no thinking in terms of the chain rule. This expression we can simply evaluate because, well, everything's in terms of u here. Look, sine u and du. We've taken the original integral in terms of x and now converted it to 1 in terms of u. And hey, that 5/3 is just a constant multiple. If we want to, we could just sort of factor it out. And then we have 5/3 integral sine u du. What function has a derivative of sine u? I believe that's, what, negative cosine u, right? So put it all together, we'll get negative 5/3 cosine u plus c. But now, rather than, oh, the plus c is off the slate here. Let me put the plus c down below. Oh, well, that doesn't fit either. Wonderful. Okay, give me 1 second here. So let's see, minus 5/3 cosine u plus c, but I've left a hole here for the u, right? Because our original function was in terms of x. So while I could technically put a u here, and I wouldn't be wrong algebraically, I wouldn't be complete in supplying a solution to our original exercise. The u in our original function here, right, was 2x cubed. And so if we write back in with 2x cubed, now we are precisely articulating the function whose derivative is 10x squared sine 2x cubed dx. If you're not believing that to be true, just take this function down here and compute its derivative. The negative 5/3 would sort of come along for the ride as a constant multiple. You take the derivative of cosine 2x cubed. The first thing you do is you take the derivative of the outer function, leaving the inner function alone, which would give you negative sine 2x cubed. The negatives would intermingle to give a positive. And then you multiply by the derivative of 2x cubed, which is 6x squared. When 6x squared multiplies by 5/3, that gives you exactly the 10x squared. So ultimately, this function's derivative is precisely the function 10x squared times sine 2x cubed. But what we have done is utilizing a slight rearrangement of our du over dx expression, we got ourselves an expression with du's on one side, dx's on the other, where we could directly substitute within our integral to get our integral from 1 in terms of x to 1 in terms of u. Admittedly, this is going to take some practice to get used to, but frankly, during the course of this semester, you will utilize integration by substitution no less than 25 times. Frankly, likely no less than 50 times. So you definitely will get practice with this over time. It's one of the classic integration techniques, and something to certainly be always on the lookout for. But when we get into class time, next time we meet, we'll go through a bunch of examples. And even in anticipation of next class, we'll have another sort of lightboard session to sort of touch base on this. Again, this will take some getting used to, but for now, we've at least got the wheels turning for how we can sort of leverage algebraic substitution whenever we have functions where there is an inside function, which we'll call u, and where the derivative of u shows up in some form or fashion, perhaps as a constant multiple within the expression of our function. For now, that's a video, and then we'll touch base on this when we meet next time.